So I think we can start now. See the question. So there is an infinite line charge having a charge density of 3 nanocoulombs per meter is located in free space at x equal to 0, y equal to 1. So we need to find out the electric field intensity at 0, 4, 0. So try to solve that. So first of all, you can put it the line charge in a diagram. So consider this is your x-axis and y-axis, and this is your z-axis. So there is a simple shortcut. When you want to represent any line charge, you can see the location where the line charge is located. Suppose in this question, the line charge is located at x is equal to 0 and y equal to 1. So x value and y value is fixed, which means that the value of z is continuously varying. So in that case, since the value of z is continuously varying, the given line charge is located parallel to the z-axis, right? So the line charge will be located something like this. Because when you move parallel to the z-axis only, x and y value will change. Sorry, x and y value will remain constant and z will continuously change. And I can see here, x equal to 0 means definitely the line charge has to be placed in yz plane. So line charge has to be there in yz plane. And y is equal to 1 represents the line charge is placed at a distance of 1 meter from the xz plane. So you can see here, this is the xz plane and the line charge is located exactly at a distance of 1 meter. So is it clear? Have you understood how to represent a line charge? Yeah. Now, in the same question, the observer is located at 0, 4, 0, which means the observer is located on the y-axis itself. 0, 4, 0, something like this. And this is an infinite line charge having a rho L of 3 nanocoulomb per meter. So what will be the radial distance here? Can you tell me what is the radial distance? Radial distance means the distance between the source and observer. Correct. It is 3 meter. See here, from the source, the observer is at a distance of 3 meter. So the value of rho will be straight away 3. So when you look at the solution, so the electric field intensity due to an infinite line charge is rho L by 2 pi epsilon rho into aero cap. Aero cap, or you can say the radial direction. So first of all, what is the direction of electric field intensity in this case? See here, this is your source and this is the observer. So the same shortcut will valid even it is a point charge or line charge or surface charge. So since the magnitude of rho L is positive here, the direction of electric field intensity will be source to observer. So it will be in this direction. So when you are moving from source to observer, there is a change in y occurred. So straight away the direction of electric field intensity will be AY cap. So I hope it is clear. Any questions here regarding the direction? So you understood, right? So find out the magnitude now. So when you consider the magnitude of electric field will be, so rho L is 3 into 10 power minus 9. And somebody is asking to repeat. Okay. See, whenever the charge is positive, electric field intensity is from source to observer. That point you need to remember. Since the magnitude of rho L, you can see here, this is a positive number. The electric field intensity is from source to observer. Source means the line charge where it is located. Observer means where you are finding the electric field. So when you move from source to observer, That means you are moving in this direction. So you are moving in the positive direction of y. So that is the reason why I have written the direction will be ay cap. Clear? Yeah. So then find out the magnitude. Rho L is 3 into 10 power minus 9 and 2 pi. The value of epsilon will be, since it is free space, we already know 1 by 36 pi into 10 power minus 9. And the value of rho will be 3 here. So you can simplify that. So you will get the magnitude will be 18, right? You can cross check everyone. So therefore the electric field intensity at the observer location is 18 is the magnitude and the direction is ay cap and the units are volt per meter. So 18 ay cap volt per meter. That is the answer. So we'll move on to the next question. There are two infinite sheets of charges and 10 nanocoulomb per meter square and minus 2 10 nanocoulomb per meter square are located at x equal to 0 and x equal to 10. Then find the electric field intensity above the two sheets, below the two sheets and in between the two sheets. So you try to put it the statement in the form of diagram. So what I try to do right now, instead of taking the value straight away, I will try to take plus rho s and minus rho s. So I will generalize it first of all. Then after getting the generalized equation, we will substitute the value of rho s will be 10. So first when you see here, one charge is located at x equal to 0. So which means that you can say this is your x equal to 0 plane. And other charge is located at x is equal to plus 10. So x is equal to 0 is having a charge of plus rho s, you can say. And x is equal to 10 is having a charge of minus rho s, coulomb per meter square. Then what will happen here right now? So the perpendicular direction for this, can you tell me what is the perpendicular direction for this? So which axis will be perpendicular to both the sheets? Z. No. No. So let me explain. You are not able to understand what is the perpendicular direction. See here. So I will generalize it in a different words. See. This is your x equal to 0 plane. To remember, x equal to 0 is nothing but a yz plane. So when you consider a yz plane, there is a change in y occurred and there is a change in z occur. So the one which is perpendicular to the plane is nothing but whichever is a constant. So when I say x equal to 0 plane, x is a constant, right? Even in the differential surfaces also, we have discussed the same thing. So when you have x is equal to constant surface, you will represent the area as a dy dz into ax cap. So where ax cap is perpendicular to the plane, right? In the same fashion, when I say x equal to 0, since x is constant, so y and z both will vary over the surface. So the one which is constant represents the perpendicular direction. So since x is equal to constant, it represents the perpendicular direction. Is it clear? Yeah. Now there is x equal to 10 means what is the meaning of that? It is also a yz plane, whereas x equal to 0 located at the ground plane itself and x equal to 10 is parallel to the yz plane at a distance of 10 meters. Base yz plane and x equal to 10 will lies at a distance of 10 meters. Even for that also the perpendicular direction is x. So right now what I have given in this is a positive charge and this is a negative charge. So first, so top one is positive x and the down one is negative x, right? So consider this is your first charge and this is your second charge. So first consider a point somewhere here. That means completely below the plates. So let me consider the point is A. So when you consider at point A, what will be the resultant electric field? I can say the resultant electric field is because of first plate plus second plate. So electric field due to the first plate means this one plus electric field due to the second plate. So what is the value of E1? So since this is of positive charge rho s, the electric field intensity magnitude will be rho s by 2 epsilon. In the previous class we have already derived that. And when you consider the magnitude, this is modulus of rho s by 2 epsilon into what will be the direction here? So when you consider because of the first charge, see the polarity of the first charge. So this is positive. So whenever the charge is positive, electric field is from source to observer. So this is the source and this is the observer. So when you move from source to observer, you are moving in the negative x direction. So E1 direction will be minus AX cap. And similarly, write down E2 value by considering observer at A itself. Now we are defining the electric field at this point because of second charge. When you are writing the magnitude remains same whether it is positive or negative, right? And since the polarity is negative here, the direction of electric field intensity will be observer to source. That means observer is here and the source is here. So you are moving in the upward direction because of the negative charge. So upward direction means the direction will be positive x cap. So what will be the resultant electric field intensity now? Magnitude is same. One will be negative x and the other one will be positive x. So the electric field intensity is 0. Is it clear for everyone?
So are we considering point A to be negative charge?
No. Point A means the observer, right? Point A where you are finding the electric field intensity. So in the first class, I already told you, wherever you are considering the electric field intensity, you need to imagine that there is a plus 1 coulomb charge is located there. A unit positive charge is located at the observer
Yes.
location. Clear?
In that case, the first sheet also is positive.
Correct.
So it will get repelled, right?
No, first thing is I already told you I will have 1 second explain. This is your source,
We'll
right?
see the
Q.
source observer. Okay.
Yeah, this is from observer. So the source is trying to push the charge of 1 coulomb, right? So 1 coulomb is trying to move away from the source.
Okay.
You got my point?
Okay.
So coulomb is not trying to attract s plus r rho s, it's trying to move in opposite direction. So that is nothing but negative x only.
Okay.
Clear?
Yes, sir. Fine. Yes, sir.
And whereas if we consider minus rho s, see here, this charge is trying to attract towards minus rho s.
Yes, sir. Okay.
So that is the reason why for the second case it is positive x.
Okay, sir. Fine.
Yeah. Can you do the same thing by considering a point somewhere on the top of both the plates, somewhere here? So consider this is point B, and you try to write down both the equations E1 and E2. Then you will get a clear picture. And x equal to 0 and x equal to 10, and consider a point somewhere on the top side, this here, point B. So this is your positive x, and when you are moving on the downside, it will be negative x. So this is my first charge and this is my second charge. So the value of E1 will be straight away, you can see here, and you can see here plus rho s and this is minus rho s. So if you are not able to remember source and observer, all these things and all, just now I explained, right? The point B is the observer, so you just place 1 coulomb charge here. So write down the electric field intensity at point B due to charge 1. That means because of this one. So magnitude remains same, rho s by 2 epsilon. And what will happen when you are at observer position and the sheet 1 is also positive? So in this case, because of the sheet 1, whatever the charge located at point B is trying to move away. So which means it is trying to move away from the source 1. So instead of attracting it to charge 1, it is trying to move away. So which means the direction will be plus Ax cap. It is moving in the opposite direction. So similarly, what about E2? Rho s by 2 epsilon into, see here positive and this is negative. So it is trying to attract towards that. So it is trying to move downwards, which means minus Ax cap. So the resultant field intensity in this case also it is a 0. And now you repeat the same problem considering the observer in between. So let us say this is point. So repeat the problem at point C. So this is your x equal to 10 and this is your x equal to 0. And the point is located here, point C. So this represents your positive x and this is your negative x. And this is plus rho h and this is minus rho s. So first of all, you tell me the value of E1. Can you tell me what is the direction at E1? Can anybody tell me what is the direction due to charge 1 at point C?
Positive x, sir.
It will be positive x.
Positive. Yes, sir.
Correct. Because see, when you see the sheet 1, since it is positive, so the unit Coulomb charge is trying to move in the opposite direction. So it is trying to move upward. So upward means positive x. Right? And similarly, what about E2? Rho s by 2 epsilon into?
Same, sir. Positive x.
Same. Because it is trying to attract towards the negative charge. So even in this case also it is trying towards positive x. So what will be the resultant electric field intensity here? E1 plus E2. So it will become, since both are additive here, so it will become 2 times of rho s by 2 epsilon. Direction remains in the positive x direction, right? So what is the magnitude you are getting here? Rho s by epsilon into Ax cap. So this is a case when you consider a point exactly in between the plates. So finally, what is the conclusion here? So when you consider a point outside the whole system, so first of all, if you see the configuration, this is nothing but your parallel plate capacitor. Yes or no? So one will be positively charged and the other one will be the negatively charged. So in case of a parallel plate capacitor, there will not be any electric field outside the plates. So the first conclusion is there is no electric field present if you consider the point will be outside the capacitive plates. And there is an electric field which exists exactly at the middle of the plates. That means when you are moving in between the plates, there will be a finite electric field. And that value of electric field you are getting right now, rho s by epsilon into Ax cap. This is x, negative x. So Ax cap means you are straight away moving from the positive charge to negative charge, isn't it? So in case of a capacitor, the direction of electric field intensity is from positive surface charge towards the negative surface charge. So is all the conditions clear? So any questions you can ask.
Sir?
Yeah.
Sir, but this is for infinite sheet of charges.
Correct.
So how can this can be related with the capacitor, which is finite, small?
Exactly. See, generally what happens now, when you are considering about infinite surface charge, you are assuming that the charge is uniformly distributed, where there are no discontinuities at all, right? But what will happen here when you consider a finite surface charge also, the approximation remains same because you practically will not get an infinite surface charge. Even the same thing is valid even if it is a finite surface charge, except there is a discontinuity at the edges. Because what will happen, till up to here, the charge is uniformly distributed, and exactly abrupt here. That means immediately after that, there is no charge because it is a free space. So the same kind of relation can be applied for finite surface charge also, except at the edges. You got the point?
Okay, sir.
Yeah.
Hello.
Yeah.
Yeah, that in practical case, that in at the edge there will be leakage. That
That
charges
is
will be
correct.
there. Right?
Yeah, that is basically called a
Oh.
leakage flow. That means when you are, suppose even I was telling you, right, in between the plates, if you are moving, the field is almost said to be uniform, right? But the moment once you close,
Yeah.
once you move very close to the conducting plate, there will be a change in practically. Ideally speaking, if it is an infinite surface charge, even if you go very
Yes.
close up to the plate also, the field should be uniform. But that will not be the case when you consider a practical case, because you cannot design an infinite surface charge. So because of that reason, what will happen practically, exactly if you are moving around the center of the portion, center portion of the capacitive plates, there will be a field will be constant.
Yes.
So that's what we
Yes.
are simulating.
Okay.
That's it. Yeah.
Fine.
Yeah. So finally, in the question, if we go back to the question, so you can directly substitute the value of rho s is equal to 10 nanocoulomb per meter square. You will get an answer, right? That I'm leaving it to you. You can do it later. So this is a question, right? Same thing we are discussing. Above the two sheets and below the two sheets, there is no electric field intensity. Straight away it is 0. And in between the two sheets, you are having a magnitude of rho s by epsilon, and direction is ax. And what you do, you substitute the value of rho s will be 10 nanocoulomb per meter square. And you consider it as a free space. If nothing is given, and you can assume that the medium is a free space. Even in your main final examination also, if medium is mentioned, you consider it as a free space. So I will move on to the next question now. So there is an electric flux density phi by r square into sine theta ar cap. Then find the flux leaving the constant r surface. So the flux density is given. You need to find out what is the flux leaving the constant r surface. So the flux density is already given. What is the value? Phi by r square sine theta into ar cap. And whatever the surface you are considering, in the question he is already mentioned, it is having a constant value of r. So can you tell me what is that surface? When you trace all the points where the radial distance is said to be constant, that forms which surface?
Sphere.
It is a sphere, correct. Because when you move on the surface of a sphere, what will happen? Everywhere you are moving at an equal distance. So if we trace all the points where r remains constant, indirectly it represents a sphere. So in case of a sphere, when you are moving on the outer surface, what is going to vary? Since r is constant, your theta and phi are going to vary. So whenever there is a change in theta, we already know the variation is r into d theta. And the variation in phi will be rho into d phi, that is r sine theta into d phi. And when you look into the direction, so whichever is constant, that represents the direction. So since r is constant, direction is ar cap. So using Gauss law, what it says? So if you want to calculate the net flux, you just integrate the flux density over the whole area. Try to find out that what is the value you will get. So since the flux and the surface both are in the same direction AR, you will get a finite amount of flux. So you can integrate it. Phi by r square sine theta into dr will be straight away r square sine theta d phi. So since it is a complete sphere, theta will vary from 0 to pi and phi will vary from 0 to 2 pi. So this is theta limits and this is phi limits. So r square get cancelled. But still you need not to you need not to simplify it again, because see the options he has given whether it is a function of r or 1 by r or 1 by r square or 1 by r cube. You can see here complete r term gets cancelled. So the final answer will be independent of r.
Independent.
So there is no dependency on the radial distance, because r square exactly get cancelled. So there is you will not get any answer in terms of r. So which means that the answer is independent of r. So any doubts in this question? So you can reply in the chat. Just moving, so move on to the next question. So I think this is what the questions I have planned for that topic. Maybe we will go to the next theory present. The electrostatics part we are going to continue. Frequency across the term electric potential, and then the potential. Finally, we will. So, four shall I plan today? I think this is the problems paper. Yeah. You can see here, first of all, when you consider a coaxial cable, it is nothing but two concentric cylinders are located arranged something like this. So this is called basically the inner conductor, and the inner conductor is surrounded by an outer conductor, something like this. So for an example, I have considered A is the inner conductor radius and B is the outer conductor radius and L is the length of the coaxial cable. So I think you would have been seeing the coaxial cable even in your houses also. Suppose if you are using any dish kind of antennas on top of your house, so there is a cable which is running out from the antenna to the television. So those kind of cables are basically, it is a coaxial cables. If you see the of the coaxial cables, it is basically there are two surfaces, something will be arranged in this fashion. So what actually happens in case of a coaxial cable was, the moment once you apply certain voltage to the inner conductor, there is a charge will be equally distributed on the inner conductor, depends on the area. So since there will be a charge distributed on the surface, for an example, we will consider the distribution of the charge as a surface charge. So I can say this charge density of rho is inner. And what will happen, since the inner conductor is charged and then you are trying to enclose the inner conductor with an outer conductor. So we already have a rigid particle is trying to enclose with an outer conductor. The equal amount of the charge also will be produced on the outer conductor with a negative sign. So for that, I was assuming that outer conductor is having a charge density of rho s outer. But what is the primary condition here? The primary condition will be the charge on the outer conductor must be equal to the minus of the charge on the inner conductor.
Hello. Hello.
So are you able to hear me now?
Yes, sir.
Yeah, we'll continue. So you can see here the charge lies on the outer conductor is exactly same as the charge on the inner conductor, but with a negative sign. So when you want to write the total charge in terms of the surface charge, what you need to do right now? So the total charge on the outer conductor will be the surface charge density multiplied by surface area. So what will be the surface area of the outer conductor here? Since it is a cylinder, we know the surface area will be 2 pi and the radius is b and the length is L. So we know that surface area will be 2 pi RH. R is and H is the length. So here the radius is b and the length is L. So the total charge on the outer conductor can be written like this is equal to minus rho r into what is the charge surface area of the inner conductor? That will be 2 pi into A is the radius and L is the length of the cable. So finally 2 pi L gets cancelled. So finally what is the conclusion you are going to get? The charge density on the outer conductor is equal to minus rho s inner into the ratio of A by B. So finally what is the conclusion here? The charge on the outer conductor and inner conductor is same, whereas the charge density will not be same. The total amount of the charge on both inner conductor and outer conductor was same with the equal and opposite sign, whereas when it comes to the charge density on the outer conductor will be the density on the inner conductor into the ratio of the radius. So any questions in this slide? Now, what we will try to do in this case was, so we will try to find out what will be the electric field intensity inside a coaxial cable. So as an example, first consider when you need to find out electric field intensity when rho is less than A. Rho less than A means you are inside the inner conductor. So inner conductor is having a radius of A. So when you consider a radial distance which is lesser than A means you are already existed the inner conductor. So can you tell me what is the total charge present inside the inner conductor?
0, sir.
What will be the reason?
Sir, because it's a metal.
Correct. As I mentioned you, the name itself I was mentioning it as a conductor. So when you consider any conductor, there are no charges present inside a conductor. So when you consider the value of rho less than A, there is no charge will be present. So whenever there is no charge, obviously there is no electric field. Correct? Now, when you consider a point, let us see the case 3 first. When you consider a surface where rho greater than, can you tell me what is the total amount of the charge present in that case?
Sir, it will be rho s inner into its surface area.
Instead of that, rho is inner into surface area of what? Inner conductor?
Yes, sir.
No. Because when you consider rho greater than B, see something like this. Can you tell me how many charges you are able to test? You are able to cover both the inner conductor and outer conductor, right? Am I correct?
Yes. Okay, 0.
Yeah. When you take a surface which is completely outside the coaxial cable, you are trying to enclose a charge which is the nothing but the charge on the inner conductor plus the charge on the outer conductor. So since the charge on the outer conductor is negative of charge on inner conductor, the resultant charge will be 0. So whenever the charge is 0, straight away you will get electric field intensity is 0.
Yeah.
So is it clear? That is basically the reason why in most of the communications, if you see whatever the type of communication, especially happening in the range of megahertz, people are preferring the coaxial cable. The reason because when any signal is passing through a coaxial cable, outside the coaxial cable there will not be any electric field, which means that there will not be any radiation. So the coaxial cables are basically meant for, it will not cause any interference to the outside environment. So that you can see it here just by the help of electric field intensity here. So when you consider a point outside the coaxial cable, electric field is 0. Now we'll try to consider a point which lies between A and B, that between the inner conductor and outer conductor. So as usual, we know that to find out electric field intensity, so let me say this is the point where I want to calculate the electric field intensity. So using Gauss law, the first step what you need to do was enclose whatever the charge it is there with a closed surface. So at this particular point, I was assuming a Gaussian surface, something like this. So this is my Gaussian surface. So this Gaussian surface is having a radius of rho. Now you can see here the value of rho lies between A and B, right? So can you tell me what is the total enclosed charge in this case?
So this time it will be the inner conductor charge.
Very good. So it will be one, when you consider this particular surface, you are able to capture only the charge on the inner conductor. So using Gauss law, what you can say, double integral d dot ds is equals to the charge enclosed. So I can say the flux density is a constant and the surface area of the Gaussian surface will be straight away 2 pi. Rho is the radius of the Gaussian surface and L is the length of the coaxial cable is equal to, so Q enclosed is same as Q inner. So we know that Q inner is equal to rho s inner into 2 pi AL. We already seen in the previous section. So what will be the flux density we'll get here? So rho s inner.
So it's not visible what you're writing.
It's not visible, huh? Oh, it's getting updated here. Okay, it got stuck. But what is coming, huh?
The only thing that's visible now is that is d dot ds. Now it came, sir. Yeah.
But audio coming?
Audio is clear, sir.
Yeah. Okay, so what I was doing it here, the flux density into surface area will be 2 pi rho L. That is the Gaussian surface. You can see here 2 pi, rho is the radius and L is the length of the Gaussian surface. And the charge will be straight away, you can say rho s inner into 2 pi AL. We already seen in the previous section. So flux density will be rho s inner into A by rho. So which will be same as your epsilon times E. So what will be the electric field intensity now? Rho s inner epsilon into A by rho. So this electric field intensity when the value of rho lies between A and B. I think it is taking some time to update.
Yes, sir.
Yeah. Just a minute, I will connect it back.